All right, now we're recording. So on page 558, we've seen this already, the surface plot command. And in MATLAB, there's an image built in, or a matrix built in that you can actually plot just by putting surf peaks. And when you do that, it gives you this plot, which is the thing that the MATLAB logo is derived from. If I can get that stupid toolbar to go away, then we can show you this here. And of course, when you get onto here, you have these tools as well. So you can use these tools to look at this. You can move the plot around, up, down, sideways, back, and you can start to see that it is trying to represent this three-dimensionally, because you can move it down and it disappears to the bottom surface of your plot window. Move it up and make it disappear up there. You can also rotate the plot and see it from different angles, and then you can start to see how this becomes the MATLAB logo. If you turn it to a specific angle, you can make it kind of look like the MATLAB logo. Trying to remember how that works. But anyway, there's some particular angle that makes it look more like the MATLAB logo. You can also zoom in on it. You can zoom out. You can take it back to where it started by hitting the home button. You can also add annotations to it, and you can actually put things on it, like you can select parts of it and so on. So there's a lot of things that you can do to this. Just about anything you could do to any previous plot that we've learned about, all those things you can do to this. And we will see some of those things today. With the rotation tool, you can actually turn this into something kind of like a contour, well, more like a, what do they call this? I think they call this a contour plot, where the shading tells you the height of things. So this brighter shading shows you something that's tall. The darker shading shows you something that's negative, so the more yellow it goes, the more positive it is, the more blue it goes, the more negative it is. And in between, of course, it's kind of at the level of the 0 point in that dimension. Let's see here. You can also mess with the shading and the color and other things like that. We have this particular function here where it actually puts it into that mode that we rotated it to. But this time, if you rotate it, it doesn't show the three dimensions. It only shows this particular contour version of it. So this is not three-dimensional. It takes the three-dimensional plot and it puts it into 2 dimensions, with the third dimension being represented only in color, not in space. So that's, they call that the pseudo color plot. So color gives you your third dimension. You can also do a shading thing here. So you can turn the shading into a flat shading. So it's not quite as, it's more pronounced shading, you could say, and not quite as linear or continuous. Gives you more stark differences. Let's see, they can do a scaled image. So image scale peaks. Okay. And this one is similar to the pseudo color, except this one is what this one has done is it's gone. So, and this one is kind of strange. This one is used a lot in when you're doing artificial intelligence or machine learning or whatever you want to call it, essentially trying to teach a computer to do something. When you're trying to teach a computer to do something, you have to simplify the thing you're teaching it to do. And this kind of simplifies the image. You can see that the pixelation has become much bigger. So in other words, each square that has different colors is, you can see the squares here. You can see those different regions of color. So what it's done is it's taken a big group of pixels and it's averaged the color over that group of pixels and replaced all those pixels with an average color. It's like kind of like blurring the picture a little bit. And this is something that computers need when they're trying to recognize faces or something like this. If you're doing facial recognition, a computer can't do facial recognition if there's too many details. It doesn't know how to do that. The details confuse the computer. So what you do when you're doing facial recognition is, instead of looking at every detail on the face, you take bigger blocks of the face and you average out those pixels and you blur the image a little bit. Because blurred images of faces, believe it or not, are actually more easy to recognize for a computer, because it takes differences and it accentuates them over a larger area and allows the computer to look at less stuff, right? So for example, the distance between the eyes, if you do an averaging, becomes much more obvious than if you don't, because if you don't do the averaging and you just have the actual picture, there's stuff like shades and the contour of the nose and maybe the bridge of your eyeglasses and things like that that confuse the computer. The computer is not very good at doing details because it's just not very smart. And artificial intelligence is anything but intelligent. It's definitely artificial, but it's not intelligent at all. It should be called artificial stupidity. But it is, this is what we have to do to make it more intelligent. There's nothing intelligent about artificial intelligence. But anyway, the point being is that this is what this kind of thing is used for. In fact, this is what many of these things are used for. Many of these tools and these functions in MATLAB were developed specifically so that MATLAB could be used for computers to recognize things, for computers to look at something and be able to learn how to recognize that. And the details of machine learning and neural networks and artificial intelligence, which are pretty much kind of all synonymous-ish, kind of synonymous. The details of that are much more complicated than I could even explain them, because I don't really understand all the details of them. In fact, I hardly understand any of them. I use it all the time. But the point is that when you're dealing with computers, you have to be able to manipulate information, including things like images, sounds, huge sets of numbers, whatever. You have to be able to manipulate them in many different ways. And this is one of the ways in order to do that, to average things out, to blur things out, to kind of remove some of the detail and leave the major features for recognition, or the major features for calculation, or for whatever else. This also happens when let's say, for example, that we're trying to track energy spikes in the energy grid out there in the United States, which they do all the time. And as you're tracking energy spikes, the problem is that the energy is always up and down. It's an AC current, so it's always going up and down and up and down. You don't want to look for the up and down part. You want to look for something that is spiking more than up and down. So you blur the picture so that the normal up and down that's supposed to be there kind of starts to blur out and fade away. And the only things that stand out are the extreme things, right? And that's another thing that can be done. You can use a computer function, a function within a computer program that you've written or that's been written by somebody else, or you can use certain techniques or whatever else to kind of extract the things that you're interested in and ignore the things that you're not interested in, so you don't waste computer time on details that aren't important. All right. Let's see, what else can we do here? Oh, okay, so that's just a basic introduction to what kind of things MATLAB can do. It can do much, much, much more than this. It would be a ridiculous, fruitless, and futile endeavor to try to show you everything MATLAB can do with images. But that gives you just kind of a basic idea. So, types of images. So MATLAB and all computer programs really can only deal with digital representations of images. So why do we differentiate digital versus, like, say, analog? An analog image is something that is a continuous representation of something in the image. So back when we were using film cameras all the time, we still have them, we just don't use them very often. A film camera had a piece of material that was usually infused with some kind of chemical, and the chemical reacted to the light when you exposed it to the light, and it reacted in such a way that it changed colors. And the longer you exposed it, the more it changed. The kind of light, the color of light that you exposed it to determined the color that the film changed to. The amount of light that you allowed in, not in time, but actually in geometric wise. So how much you opened up the camera, which was called the aperture, determined essentially the brightness of the colors that showed up on the film. And all these things were very continuous. If you let in twice as much light, you would get twice as much brightness. If you opened it up for twice as long, you would get twice as much exposure. If it was just this way. If something was twice as red as something else, you'd get twice as much. And it's the same if it was 1.5 times as much, or 1.7 times as much. The reaction of the film was very analogous to what was actually happening. If you had 7.5 times as much light, you had to have 7.5 times as much exposure on your film. Digital images are not that way. A digital image is an image where you expose a microchip or some kind of a sensor, which is usually some type of microchip, pretty much always actually, some kind of a microchip to light, and the microchip detects the light differently because it's a solid state device. Solid state device means that it is that its reaction is quantized, or quantum mechanics governs how it reacts. Now, the science of that is well beyond this class, but suffice it to say that when you're dealing with a solid state device where the atoms inside this microchip react very specifically to specific kinds of light, you could give it twice as much light and it won't necessarily react that way. It won't necessarily react with twice as much exposure. It is actually, it's very sensitive to certain things and less sensitive to other things. And they've tried to improve them over time, but it's still a quantum mechanical device. And so it ends up having pixels. Essentially, each device has a certain number of miniature devices in it that are all connected in this big array. And each one of those miniature devices reacts to the light that hits that device, right? And it's quantized because you can't say that there is an infinite number of these things, because you can't have an infinite number of things. It just can't happen. Each one of these devices in the chip is an individual device connected to another individual device. And they're super tiny. These devices that constitute the pixels on these chips are very, very tiny devices, but they are devices. And so they have a limit to how small they can be. So you have a limit to how many you can put into a picture and how close you can get them together. And so digital images are always limited in that fashion by the electronics, essentially by this little piece of hardware. The film cameras were limited by their optics. They were only limited by how the optics were built. So film cameras usually had a ton of really expensive optics if you wanted a good camera to get that high quality, high resolution, high focus kind of image. And also, if you wanted a better resolution, you would just get bigger film. Bigger film, you could put smaller objects on and still be able to focus them properly with the optics you were using. So it was more of a mechanical and optical issue when you were dealing with old cameras, these old film cameras. But these new cameras, most of the problem that you're dealing with, most of the limitation is in that actual chip. because of the size of these individual devices. And each one of these individual devices cannot, they can only, how do I say this without going too far into the science? To these devices, light is like a particle. To the cameras of old, light was like this continuous wave of energy that came in. So if you got a little bit more of it, you'd just react a little bit more. But to this device, to this chip, light is like a bunch of baseballs coming in. And you don't need to know why it's different. It just is different. There's no denying it. There's no explaining it away. It just is. So you can only have, if you throw one baseball at it, it will count one baseball and it'll react like it got hit by one baseball. You throw two baseballs, it reacts like two baseballs. But you can't throw 2.5 baseballs at it. There's no in between there. There's no, so the variation of this thing is a stepwise thing. So you don't get as much variation. You don't get as much as clean of an analogous picture, and that is the limitation of your digital devices. Now, digital cameras can reach a very high resolution. They can reach a very, very good quality image. But the fact of the matter is that they will never be able to reach the quality of a film camera. It's just not possible, because a film camera, you could just make bigger and bigger if you want, and they made plenty of big cameras. That won't do any good for a digital camera. You can make it so high resolution that your eye can't tell, and that's pretty much where we're at this point. At this point, the digital cameras that we have you can't tell the difference between a digital camera and an old high quality camera anymore with the naked eye. You'd have to really zoom in on it with something, some microscope or something, because our eyes just don't have that much resolution themselves. Our eyes are actually more like digital cameras. Our eyes have individual little things called cones that detect individual photons or individual particles of light. So our eyes are like digital cameras, not like analog cameras. So once you get them smaller than the cones in our eyes, then you're at a point where you can't tell with your eyes where the pixels are. The whole point of that is that digital images can be represented as matrices because they have individual things. They have these quantized individual pockets, which each one of those quantized little things that detects the light gets its own little space in the matrix. And that's easy. You can't do it with analog pictures because there's no organizing that. You'd have to, if you have an analog picture that you took with a film camera and you want to make it digital, what you have to do is you have to go into that picture, you have to split it up into a bunch of little boxes, and then you have to average the color. Sound familiar? We just did this, right? You have to average that color and make it a digital pixel, and then you can digitize that photo if you do that for however many pixels you want in the picture. And that's what scanners do. That's if you scan a photograph into your computer, that's exactly what they do. In fact, that's what your camera does. If you take a picture of an analog picture and a picture of people, whatever else, it just does that. It takes, let's say I'm looking at Jason's face, and I'm going to take a digital picture of your face. What I'm going to do is I'm going to go up in this corner. I'm going to say, oh, up in this right hand corner, that's not Jason's face. That's the white wall behind it. It's not really white. It's kind of, because it's grabbing that cabinet too. So it's got a little bit of white on the right side, a little bit of kind of tan from that cabinet. And then I go to the next box. Oh, that's all wall, and it's all that whatever, off-white, white color it is. And then you get in here and you're like, oh, look, there's that poster. And so you go from white to the black in the poster, and then in the middle of the poster is some blue. And you do that all across the first row, and we haven't got to your face yet. And then you do that again, row and row and row. Finally, we get here to the edge of your face, and we're like, oh, look, there's a little piece of that dark brown hair he's got there. There's a little piece of it, but behind it is that white wall again. And so you're averaging each one of those pixels, and you do that all the way across your face and all the way across. Every little bit of your face is a slightly different color because light's shining off it, or just pigmentation differences or whatever else. And every little pixel gets its own little spot in the matrix, and that's how you make a digital photo. Simple as that. Not really that simple, obviously, but it is simple, and the idea is simple. And that's what it is. It's just a matrix of numbers that represent the colors as we scan across a particular image, right? So that's why computers can deal with them, because they're just matrices. The different types of these determine how the matrix is made. And so you've heard of many of these probably. You've probably even heard of all of them. The first one that they talk about here is the intensity images. Let's see, yeah, intensity images. So an intensity image is the simplest type of these. All it does is it looks at how much light is coming in. It doesn't care about the color. So this is going to be a black and white image, or a gray and like a grays and whites image. You have essentially white and black and all the gray scale stuff in between. So it's a grayscale image, right? So that's what we call a grayscale or intensity image. And the matrix for that is simple, because what you need for a grayscale image is you need essentially a pixel for, you need a cell or a part of your array, an element in your array for each pixel that tells you how much you're going to go from one end of the spectrum to the other. Your spectrum is white on one end, black on the other, and everything in between is some version of gray, dark gray towards the black side, light gray towards the white side. And then you have a set of numbers that determines how gray or how dark gray you're going, or how light gray you're going. And then at the extreme ends of that, there's one number that says this number is white and this number is black. Maybe white is 0 and black is 100 or something. And if you want more numbers, that just gives you more intensity difference. So if you have one, if you say, let's say that 0 is white and 100 is black, right? And you want more variation, that gives you 101 options for variation. If you want more variation, just go 0 is white and 1,000 is black, right? And it doesn't really matter which end you put white and black on, you just have to tell the computer, right? So that's kind of the idea of the intensity image. So here, let's take a look at an intensity image. We have, I think they have one. I think they have this one built into MATLAB somewhere. Maybe not. I don't think so. Let's check. That looks like it does. Looks like it is in there. So, so apparently there is this image built into MATLAB called Spine, because it allowed me to do it. It didn't give me any warnings that it's not there. And then I'm going to do image. And I'm going to do, so what it did is it loaded is this thing X. Let's take a look at this thing. Come on, open it up already. There we go. So this is it. It's rather big. Oh, there's some numbers. All right. Well, let's go and see what this looks like. If I do a scaled image of this, this is what it looks like. So this is an image of somebody's spine. This is kind of an X-ray, it looks like, or maybe, yeah, it's an X-ray. And we've just loaded it and showed the scaled image version of it. We can also change it so that it looks more like a traditional X-ray. And we can do that by using the bone color map. So we'll use the color map command and choose the bone color map version here. So that looks more like a traditional X-ray. It's just a different range of colors for the numbers that are selected, right? MATLAB knows how to change it to different color shadings. You can choose anything you want. It can be multiple colors or single color. This one is more like just black and white mixed together, right? The other one looked like it was more like black and yellow, or sorry, blue and yellow and maybe a little orange mixed together. But those are just colors that have been assigned to numbers. That's all it is, really. Right? The color map is just a list of numbers and colors that are associated with those numbers. And then when these numbers show up in a matrix, it just puts them in, calls it good. It's that simple. So that is the idea of this first type of image, the intensity image. Now, you can actually search on Google for intensity images and find many of them. There are all kinds of them out there, and many of them are digital x-rays like this, actually. But the more common types of images that we deal with in everyday life are things like JPEGs. You've all heard of JPEGs, I'm sure, right? So a JPEG is another type of image that is a matrix of numbers, essentially. The types of images are not only how the matrix is built, but it's also how the image is converted from an image that it may be more analog to an image that is digital. So there are different ways of making the matrix, but there's also different ways of representing the original image or the original object. You can think of it as how the computer interprets what it's seeing when you take the picture with the camera. So that also has to do with some of these things. So the next one is the JPEG, and we're on the top of page 561. We're going to go look for this image on Google, or an image like it, of a moon. This is the Mimas moon. So we're just going to do mimas.jpg like that. So here is a nice JPEG image of Mimas. Of Saturn. This is an interesting one because it has this huge crater on one side that is visible from Earth even. Insanely huge crater. It's like a tenth the size of the planet almost. Here's a nice picture of what Mimas looks like compared to Saturn. Saturn is quite large. There's another picture of it. So anyway, we're looking for a JPEG image of this. So we go back up here to the top and grab one of these. They have several of them at Wikipedia, Wikimedia, I guess that's called. Here's Wikipedia, here's Wikimedia. They have one at NASA. We'll grab, I think I like this one best from Wikipedia. So lots of different ways that you can pull this off the internet. You can just right click on it and go ahead and save image as. You can put it into your downloads, or you can put it directly into your documents in your MATLAB area. So I'm going to go right directly into my MATLAB folder and drop it in there so that it's in my workspace that I'm dealing with. And then I can do this im-info and ask for some information about the image. I have to put the name of the file, which is the name of the picture, in quotes. I think it's called mimas.jpg. Let's check to see if that's true. Let's see, I'm in the wrong folder. Let's go back here. It's Mimas Cassini. So that's the name of it right there, actually. Capital M. Mimas _ Cassini .jpg. Yes, that's what I, no, that's not what I meant. Yes, that is what I meant. Info, not im-info. There we go. And it can actually give you information about that image. Now, why can it give you that? JPEG images actually store a lot of information besides just the actual image itself. So it's got date and time in here, right? This is the time that the image was created. And this, it'll even tell you that it was made with a digital camera, gives you resolution, software, all kinds of stuff here. So coding process, there are different ways to create JPEG images, and this tells you the code that it's used and the method that was used to do it. Tells you the color type. It tells you that it's a grayscale image. It's not storing color information, in other words. Tells you the width and height of the matrix, essentially. This is the number of pixels here, wide and height, and then the bit depth, which tells you essentially how much information is stored in each pixel, and so on and so forth. So lots of information here. Even tells me, because MATLAB stored this information, that it tells me where it is and when I downloaded it, essentially, and the size of the file. That's all information that MATLAB stores when I downloaded it and my computer stored. But the rest of this information is information that's actually built into the matrix that is called Mimas Cassini JPEG. So JPEG images can be quite useful with all that extra information. They're a great storage place for data. If you have images that are related to specific things that you're studying or specific things that you're doing, the JPEG image can store that data for you, and you don't have to have a separate file saying, well, this picture is this, and this picture is this, and this picture is this. The image can store that data for you. It actually has room in the file for it. All right. Then you can actually do some things with that. So we'll use the image read function, and we're going to actually set this equal to X. So now we'll say big X is now going to equal image read. And we'll use the same file here, mimas underscore .jpg. You have to do the .jpg in there, I believe. Look at that. It's essentially read off all of that. It's printed it to the screen. It's a lot of numbers. Remember, this thing was 1800 by 1800 or something like that. It's a huge matrix. Right? And we should also be able to show it. So we'll just do the same thing we did before, image SC. Now we've actually read this thing into MATLAB. It should show up as X. Well, of course, it showed up as X before that, but we can do a scaled image of this because it is grayscale. Oops, I did that wrong again. Just misspelled it again. And we can actually plot it out. This is actually not any different than a plot that we did of, like the sine function. It's just another matrix, and it's just plotting point for point. It just happens to be point for point a plot that looks like the moon Mimas. Actually, I don't know if it's pronounced Mimas. I've never really looked it up. Never heard anybody else say it. You can also change the color map on this one. The JPEG image actually already has the color map built in. So it tells MATLAB which color map to use, but you can change the color map. You could change the color map to, trying to remember some of the names of the color maps. Can't remember. Color map. What color maps are there? Parula. Is that a color map? I've never heard of that one before. Let's try it. Yeah, there's a color map. You could change the color map of it so that the numbers that are in the matrix now mean something different to MATLAB. Instead of being a bunch of different grays and blacks and whites, it's greens and yellows and oranges here and blues. You use the image scale command again. So the scaled image, it's image SC and then put in the X. Oh, to read it in? You don't actually have to read it in to do that. Reading it in prints it to the screen here. But when I did it, I lost my thing. I lost the previous command. It's this one. You can either do you can either use the image info. If you use the image info command, it will save it to this big X thing. Or you can do big X equals image read right about 2/3 way down page 561. Either one of those will set this equal to X. So this is what it looks like. If you do im info like this, it's inf info, and then you call the file. So that would be mimas _ Cassini, like that. If you do this, and our workspace over here, if I go ahead and delete this variable from my workspace, so now that's not there. If I do im info mimas Cassini and hit enter, let's see. Did I info? What's that? IMI. Oh, inf. No, it should be inf info, right? Inf info is correct, I believe. Oh, and then I forgot to put JPEG. You have to put .jpeg. That's what I did wrong. So you have to do .jpeg. So what that does is, well, the last time it did, and it didn't do it this time. But this one gives me the information, and then when I do the image read, I can set it equal to capital X. So X equals image read, im read like this, and I can put in the same thing, which is mimas _ Cassini .jpeg this time, and I'm going to suppress the output this time. But what that does is it actually reads through the matrix one element at a time and reads it into MATLAB and then stores it in a matrix called X. And then X over here shows up as this big matrix of numbers that represent colors for whatever color map. And then to actually print that into my figure window, to actually make a figure out of it, then I'm going to use my scaled image command, which is image scale, so image SC, and then you just put X in there. But you could also put mimas Cassini.jpg, and I've still got the same color map on, so it's still printing to the screen as blues and yellows and things. Oh, to change the color scheme, you go to color map. So I used color map per whatever it was called, I can't remember. You could use the bone color map. They're just different names for the color maps. And if you want to know what those different names are for the color maps, go to help color map. And then I would, so here's another one. Caxis is a different color map. There are lots of different color maps, and you have to look them up to figure out what they all are. Here's the reference. Go to the reference page for color map and open that help page here. And it'll tell this should give you all the different color maps and kind of what they are. They should show you some examples. So this color map is the winter color map. It's blues and greens. This is the summer color map, which is greens and yellows. This is the default color map, which has the blues going to yellows with oranges in between. And then they have, so I don't know what this one is. Probably autumn, who knows? So they have the Perula color map. You can actually create your own custom color map by choosing which colors go in different intensities. See what other, here's the autumn one, actually, the autumn color map. There are literally just tons of these things. Here's the pink color map. No, this is the hot color map. That's this hot one. This is the pink one. It's all pinks and kind of yellowish things. Here's the bone color map that we saw before. And here they show all the color maps. So what these color maps, what this is telling you, what this chart is telling us is it tells us how the colors change according to the numbers. So for Perula, when the number is 1, I think, when it's 1, it's blue. When it's 100 or at the maximum, it's yellow. At the minimum for jet, it's blue. And you can see how it changes as it goes through. The Perula changes from blue to kind of light blue to kind of light green to kind of light orange to kind of yellow. And if you go down here to the cool one, it starts at light blue and it goes into kind of a darker blue and then kind of a purpley thing. And then it goes to definite violet. So these color maps are just different ways of representing the intensity numbers. That's all they are. And sometimes it's just done for style, but sometimes it's done for a particular reason. There's particular reasons for choosing a color map. I have no idea why anybody would choose these color maps, but they do. Here's the white color map. It's just white all the way through. That's not very useful, but sometimes it's done anyway for some reason. So those are color maps that are predefined apparently, but you can actually make an infinite number. You can create any color map you want. It's completely up to you. You can design them any way you want. Usually the picture that the image that you open has a color map that it's designed to be opened with, and that's in the file. So the computer reads that and then displays it with that color map. For example, the moon picture is built in with a grayscale color map, and so unless you tell MATLAB to do something differently, it'll open with that. Since I had my color map set to a different thing, I had it set to Perula, it came up with a different color, but you have to force it to do that otherwise. All right. Any other questions about JPEGs and kind of what's involved with JPEG images? So we're actually going to get to some other types of images here. Not all image files are not all the same. They often have the same information, but not necessarily in the same places in the same ways. So you sometimes have to treat them differently when you're doing manipulations and other things like that. And sometimes even opening them has to be done a little bit differently. MATLAB has, over the years, tried to create a single method for looking at images, but still it's not always cut and dry. And that will actually come up here in this next one here. This next one we're going to be doing is our indexed images. Now, indexed images include, I believe, GIF are index images. I believe TIFF are index images. Because the TIFF and the GIF stand for graphic index file or something like that. Or I can't remember exactly what it stands for. But I believe that those are both indexed images, GIFs and TIFFs. But there's also, let's see what other kinds of images are out there. There's JPEG, GIF, TIFF, PNG. And each one of them is slightly different. So And even GIF images and TIFF images aren't always indexed images or indexed files. They're not always stored as index files. They don't have to be. So sometimes you have to kind of learn more about the file that you're opening to before you can really mess with it. But anyway, we're going to load another file that I believe is actually already into MATLAB, so we'll try that. We're going to load this thing called mandrill. So we're just loading a matrix of numbers in, and you can see here that it's put it into this thing we call X. Whenever you load something in, an image file in, it just loads it as big X by default, unless you rename it to something else. That's what it's going to be. So it's replaced our Mimas thing here. The X that used to be the file that had our Mimas moon in it is now got this thing in it, and we can actually display this. So there it is. That is our mandrill. So a mandrill is kind of like a baboon kind of thing. And we're seeing this in a grayscale or a black and white scale or some kind of scale that is not the color map that we're necessarily interested in. So what we're going to do is we're going to change that color map. We'll do a color map map like that. Now that gives us a little bit more interesting image, but it's not necessarily a true image of what it is. Also, you have to be aware of the scaling of your image. You can see here that this side of the image is scaled from 0 to 450 and then a little bit more, so it's 500. And this one is also 0 to 500. So these two sides should actually be equal in length, but MATLAB doesn't make them equal in length. You have to make them equal in length. So you can either drag it like that. There's also a command for making them exactly equal in length, but that would be more like the realistic picture when we'd use the color map. The way to do it with a MATLAB command is to do axis image like this. And in this particular case, what axis image does is it looks at the actual it looks at the dimensions of the array, the dimensions of the matrix of the image, and then it adjusts the image window, the figure window, to fit that. So this is a perfectly square image window to fit this perfectly square image into. So that's what it should actually look like. Yeah. What else do we want to do here? Can't think of anything else we want to do with that particular image. Let's move on to a different type of image. This is an image that is a GIF image, which is also an image that can be stored as a indexed image, but we want to see if it is. So what we're going to look is we're going to look for the image info, doing the info again, and we're going to actually actually, I don't think this one, I think I'm going to have to download this image. So let's go look for a GIF image because I don't think this one's stored in MATLAB anywhere. Let's look for a GIF indexed image. Indexed image. So this one looks like it's a GIF image right here, but it looks like it's two images in one. So I don't think that's going to be very helpful. But here they have just the single one, looks like. So this is the single image. So if I save this image, I'm going to save it as, they call it Lena. So we'll call it Lena. And it's saving it. I'm just going to save it like that. And let's put it in my downloads, I think. Let's take a look at the download and see what how it came up. Maybe it didn't. Maybe it saved it into my MATLAB. Don't know. It did. Oh, so it actually saved it as a JPEG. And the reason for that probably was because I just right clicked on it, and I think Firefox just automatically converts things you right click on to images. So I'm actually going to open this up in ResearchGate, which is a research site. And let's see if the image here is actually, if they have a file to download it here somewhere. No, it's actually a JPEG here. So that's a little bit, that's not good. It's not going to help us. Turns out that's not from a very reputable source anyway. All right, let's go back to, let's close this and go find a different GIF image. Let's see if that's a GIF image. Yeah, this looks like it actually is a GIF image. Yeah, I hope. Let's see. Oh, shoot, I didn't. What did I? So GIF images can be animated, but they are not necessarily animated. So the GIF format has the ability to store multiple matrices that represent movement. So it's essentially just multiple pictures that are shown one after the other, right? So an animated GIF is not actually like a movie. It's just a bunch of images stored in one file, one folder. And then when you look at them, they just show you one of them, one after the other, one after the other, and they just repeat them one after the other. It's a very simple animation, you can think of it as. GIF has that ability to do that. Many other things have that ability as well. Many other image files you could do that with, but GIF is just kind of designed that way. So it looks like we were calling it this here, and what was that image of? I forgot. A bird, so we'll call it bird. Bird.gif. And so now what I'm going to do is I'm going to go ahead and look at the info of that. Info of bird.gif, and we'll see if it is what we want it to be. We want it to be an indexed image. And if we look through here, we can see right here that the color type is indexed. Okay, so it is an indexed image. Is because it is an indexed image, it will have the color map built into it. So there will be a file in here that will have the color map that is supposed to be used for this. And the color map will be under that name map again, because remember we used color map. So we should be able to use the correct color map for this one as well. So we go ahead and do the same thing we did before. Hopefully, it looks like they don't do that with theirs, but it's okay, we'll do it anyway. Let's see if, how do you get this bird in there? So did you find this file? So what I did here is I just right clicked on it and I saved the image as, and then I saved it in my MATLAB file in my documents. And then once I saved it in my MATLAB file, then I went to MATLAB and it showed up here in my folder, my MATLAB folder. So go to my documents and then go to MATLAB, should be under your documents, and then just save it into that folder. So now that I have that image in here and I've looked at it, I've looked at the information, it's an indexed image. So it's going to have, so it's not only going to have the matrix of numbers, but it's also going to have a color map matrix in there that tells you what colors to assign to what numbers so that the colors come out correct, right? Or, you know, as correct as a digital file can. Then you can go ahead and try to show that image, and you would show it using a very similar code here. You can use this code here, image X. Copy that. Now this is our new image here. I'm going to paste this down here. Oops, it didn't save it. We actually have to load it. Sorry. Actually more similar to what we did before here. So we can do we'll do the image read. We'll actually do this actually will be image. Is it imread or image read? I can't remember. Imread. Imread, there we go. So we'll go ahead and imread this thing in, which is called bird.gif. And you can see it comes in as this big old group of numbers. Now, now we can go ahead and, well, actually, we should probably assign that to X just to make sure it gives us the right thing. Read bird. Don't think it's changed that .gif. There we go. Now you can see that X has changed. Instead of being 480 by 500, it's 322 by 365. It's a different matrix in there, and it's this matrix of numbers that is our matrix for the bird, right? Now let's use two different methods. We've been able to look at the images or plot the images. You can think of them as using two different functions. One of them looks like this: image scaled. So you have image scale. If you do an image scale of X, which is our bird thing now, it looks like this, right? And a scaled image is not reading the color map. But if you just do image, it should look different. Does it look different? You can't tell. A little bit, right? Because it's using a different color map. Now, if we do image again, and then change our color map to the map that is actually included with this file, it should change it. Oh, dang it. Oh, because I did it wrong. You have to put this in parentheses. Color map. That should actually have changed it back to its thing. Let's do this again. Image X and then color map. And that should have changed it, but apparently it's not reading the color map for some reason. Did it change the map when I changed X? This is the map for our color map. Let's see, X equals, actually, let's do this again. I'm going to go back and see if it changed the color map. I had before Mimas underscore Cassini .jpg. This one had a different color map. Didn't change that color map. So this is actually the incorrect color map. I don't know why it won't change the color map. Oh, I think I know what I did wrong. Okay. Now let's try it. If I'm right. Um, nope. It's not reading the color map, and I don't know why. Hmm. Map. Well, I don't know why it's not reading that color map. It should, but it's not. And it doesn't show any example of that for the GIF image. We have to do some research to figure out why it's not showing the color map of the GIF. Let me try this one more time here. If I insert this one, oh, I see. I think I know. Let's try this. Load. Um, doesn't have the file there. So I guess this one actually must not have its actual color map with it. That's the only thing I can conclude. Oh well, I guess it's just not there. Picture's there though. That's okay. I'm gonna try one more thing. I think I keep just doing something that I shouldn't do. Okay, so let's actually load let's load this image in differently. On the top of page 564, they show another way of importing an image into MATLAB, which is to use the image import wizard, or just the import wizard, I guess. So if we go to import data, it opens up an import wizard, or it opens up this thing that you can click on, and then you can open an import wizard. And it's like click on bird.gif and open it. Here's the color map. There it is. So here's the data. The data is actually the pixels. Those are all the values in each of the pixels. This second part is the color map. And that's the thing that I was looking for that I wasn't able to extract. And this way you can extract it. So I'm going to import both things. I'm going to, and we're going to go ahead. Now this one, they're going to import with the name color map, which I probably don't want to call it because MATLAB already has a function called color map. So I should probably just call it map like I was saying before. And this one I'm going to call bird like I wanted to before, like I had it before. So I'm going to replace that with the name bird. And then I'm going to go ahead and finish that. And then you can see that now we have this thing in here called bird and this thing called map over here, right? So let's go ahead and plot bird as an image. Now this time I don't have to give it any kind of quotes around it or anything else because it's already a variable in MATLAB. So I can just plot it. And that's the one we saw before. But now that I've imported the color map, because I figured out where it was, then I can use the color map command and use the map, the thing called map, which is the color map for this particular image. And then you can see the colors there. So that demonstrates more about the indexed image. The indexed image has this index file of numbers that relates to the color map file so that you can use the color map file to plug in the correct colors. That's the basic idea there. The last one that they talk about are true color images or RGB images, where instead of having a color map that corresponds colors to numbers, it has a red, green, or blue pixel. So it's like you have this matrix that has rows and columns, and then in each cell of the matrix, there's what do they call that? Not a drawer, but they call it a page, right? So each one of those has actually not a page, but 3 pages. One of the pages contains a number for the brightness of the red pixel. One of them contains a number for the brightness of the green pixel, and one contains a brightness for the color of the blue pixel. So you get RGB, which is considered true color. And then you can mix and match brightnesses of those pixels together to make any color in the rainbow, essentially, right? So this is the JPEG gives you a closer image to like film images. It's the only downfall is the fact that it is pixelated, but it gives you a very, very wide range of colors. The color map that we just saw on the previous picture with the bird, if you look at this map, you can see there are only 256 different colors. There are 256 essentially rows in this, and that corresponds to each one of those rows corresponds to a different color. So you have only 256 colors available there. In the RGB, you have, I mean, in theory, infinite. It's not infinite, but in theory it is. But you had to have a lot more options, many more options. So RGB is usually called a true color type, and if we look for an RGB image, those are JPEG images are often RGB images, so we can find just about any JPEG image. Here's a nice RGB image, except that one's an image of an image, it looks like. Some exploding paint, maybe, who knows. Here's a nice, this is a hot image. Chili peppers and garlic and regular peppers and tomatoes. It's like a salsa bar. Here's one from MathWorks. There we go. Where did the image go? Here it is. So let's save that. Let's see what it saved as over here. What was that thing called anyway? Peppers. Okay, that's easy enough. So did it show up here? Yeah, there it is. So that actually came over as a GIF, but let's go ahead and look it up anyway. Let's get the image info on there. Info of peppers underscore CMYK.GIF. So what CMYK stands for is cyan, magenta, yellow, black. So cyan, magenta, yellow is the same as red, yellow, or sorry, cyan would be blue, red, yellow, essentially, right? RGB being red, green, blue. It just kind of just depends on how you define the numbers. The cyan is the blue, the magenta is the red, the yellow is the yellow, or the green. Whatever. So let's see what we can get for the information from this thing. Whoops, I did that. I suppressed the output, which I didn't want to do. So the so this one is actually indexed color type. They say that it's a true color, but it's not. It's an indexed one. So that's no good. We don't want that one. True color images. Where's the true color image? Well, let's go find another true color image. True color image. Ah, I love these ones. These are great. Here's an earth and true color image. Love it. Save image as. That's a big thumbnail. That's not what I want. Mission. Why can't I get the data? Where's the data? Imagery and data. All right. Download imagery. So we can decide what we want to look. Geo color map, infrared, water vapor. We want to see, I don't want to see country borders. I don't want to see merged. Well, I guess I do want to see that. Let's see, turn all layers on, turn all layers off. Okay. All right, so let's see if we can actually download this. Move down, description. How do I download? Anybody see how I can download this? They said that I could download from here, but I can't see how I'm going to download from here. Maybe take a picture, camera, capture and save an image. Click on the map and draw on each side of the box. Okay, and then once you select the area, click save on this splash screen, wait for download. All right, let's click on the map. Yeah, let's get out of this thing, I guess. Click on the map. Try again. Click on the map to follow these steps. Click on the map to draw and resize the box around the area that you would like to capture. You can move this splash screen out of the way as you use the tool. Once you have selected the area, okay, so you have to have this thing open while you're doing it. So this is the Nebraska area-ish, right? It's also covering part of the mountains and all the way out to Missouri. Start, I might go to finish. Okay, click save on this splash screen. So this is interesting here. You can download the GIS data file. So in this case, I don't want to include land borders, and I can also choose my resolution for 1 kilometer per pixel here. So if you zoom down to 1 pixel, you would only see North Platte would only show up as a set of maybe 12 or 15 pixels. It's not, North Platte's not that big. So it would show up at very low resolution. If we wanted to go, we can't go any higher resolution. That's as high resolution as it goes. We go bigger resolution. We can go lower resolution, bigger numbers, higher resolution, lower numbers. We'll keep it at that. 3.9 megabytes. But we could also download the GIS data, which includes in the picture the geosynchronous satellite, or the, what do they call that? Whatever they call it. But your GPS coordinates is what it would be. So image files can actually include GPS coordinates for every single pixel, which of course can again be very useful, because if you're trying to match data in the picture, maybe you're taking a picture of crops, for example, and you're saying, well, this part of the cornfield at this pixel is looking kind of brownish yellow, and this part of the cornfield is looking kind of green. Then you know where to put the water, right? And that's actually something that I'm doing in my research. We're actually using satellite images and airplane images of fields and trying to teach a computer to look for the places that need water so that we can tell the pivot where to put the water. Because with these great big pivots, you can actually tell it where to water in the field and where not to water. And so if you can have a computer do that, then you can save water. You don't have to use as much water out there, and water is expensive when you're growing things. So anyway, we'll go ahead and not include the GIS data for now. Well, maybe we'll just include it. And then we'll save this thing. So it's retrieving this image that is in, that should be a, this should be a true color picture because they said it was going to be. So let's assume that it's going to be. And it looks like they put it in as a ping. So this is another different kind of image. And in science, when you're doing science images, it's almost always a ping. The reason for that is JPEG has one serious problem with it. Every time you open or read a JPEG file, it changes the file slightly, which degrades the image. It actually changes the image a little bit. And it's not a change that you can notice, but over time, it will eventually degrade the image significantly. So JPEG images are not great for multiple uses and opening over and over and over again, okay? Which is unfortunate since most people save their like family pictures as JPEGs because cameras usually save them to JPEGs. And the reason for that really is just because people recognize it, it's an easy file to deal with. But really we should be saving them as pings in my opinion. But this should be this one should be a true color photo. So let's go and see if it is. Let's put it in documents, and then I'm going to put it in my MATLAB folder here. And then I'm going to go to MATLAB and see if it actually is a true color photo. So I've got this folder in here. I'm going to go ahead and open this up, and then I'm going to import this data in. I'm going to import this ping file. So it's in there. All right. You can see that it's three-dimensional. So this is a true color, right? This thing is true color because it's three-dimensional. I should be able to look it up as well to see if it is true color. It's A, B, I, GC underscore last underscore 24 hour underscore limit I don't know if it's going to allow. So there's there are your GPS, some of your GPS coordinates there. That's some of your GPS data. I'm not sure if it'll allow that in the name of the file. We'll see if it allows that. I don't think it will. Yeah, so we have to take that off actually. I think that that actually doesn't belong in the name of the file anyway. And if it does, then we won't be able to use this. No. Okay, we won't mess with that, but let's see if we can plot this. We know that it's a true color image because it's this three-dimensional file, that third dimension representing each of the red, green, and blue pixels. So let's see if we can go ahead and open this here. It actually put it in as a very different thing here. So there it is. Comes through as a true image file. A true color file. You're seeing the true colors of Nebraska, which is exactly what Nebraska looks like in the late winter, right? Just a big brown flat thing with a little bit of snow here and there and some clouds over the top. So, all right. And of course, this one has no need for a color map of any kind. And you can change the colors in this. It can be done, but you're not going to do it by changing the color map because there's no color map. This just has these different pages in each pixel, you could think of it as, that correspond to the brightness of red, the brightness of blue, and the brightness of green. And those three things in each pixel can be mixed to make any color. You can have different amounts of red, green, and blue in each pixel that correspond to a different color of any kind, including brown. Whereas in the others, in the indexed files, you had a number that was light brown. You had a number that was dark brown. You had a number that was green. You had a number that was lime green. You had a number that was aqua. You had a number that was pink. You know, there was a number corresponding to to a whole bunch of different colors. And you had a limited number of colors, and they were specific colors, and each pixel was a specific color. In this one, every pixel is a mixture of three colors that gives you pretty much any color at any pixel. It's almost limitless. It's really the only thing that limits it is really the computing power of the computer. So that's a true color image. In this case, we have a true color ping image. There are true color RGB images. So that is that. Now, let's go ahead and take a bit of a break here. Just take about 5 minutes. It's already 2:45. Let's take a 5-minute break, get a drink, walk around a little bit, and then we'll come back and cover the rest of this. Oh. Help yourself to soda. All right. Okay, I am remembering at this point that I actually usually take 2 weeks on this chapter because we're getting to this point here where we're going to stop talking about images and we're going to start talking about dealing with plots again. We're going to do some work with plots again. And the work with plots starts right about 572 and goes all the way until 590 something, 590. So it's pretty involved now that I'm remembering it, because and there's a lot of code involved. So we're not going to actually finish this chapter this week. We'll finish all the way up until we'll essentially finish just the first section today, 14.1, and then we'll save everything else for next week, and we'll spend another week on advanced graphics. So and one of the reasons for that is because I want to go through this example 14.1 at the end here of 14.1, right where we were ended on page 566. And the reason I want to do this is mostly because it's interesting. People find it amusing, and I'm going to give you some homework on it. In this example, they create some images, some plots of Mandelbrot and Julia sets, and these create what are called I always forget the name for these in math. It's a recursive algorithm plot called let's look it up and figure out what it's called. Recursive function plot. Recursive function plot. It's called a why can't I remember? Fractal. That's the word for it. They're called fractals. So you may have heard the word fractal before, but I always forget the name of it. I always forget the word. And if I remember the word fractal, I forget that it's a recursive algorithm. I forget the word recursive. But anyway, these are called fractals. And the idea behind fractals and recursive algorithms, recursive functions, is that you have some kind of mathematical representation, some kind of mathematical function, where within the function actually uses itself to calculate itself. It's kind of like a chicken and egg kind of thing, where a chicken lays an egg with a chicken who has got an egg that it's laying. It's a weird thing. It's recursive algorithm. Another way that I've heard recursive algorithms explained is imagine that you're walking on some stairs, and you're trying to determine that the stairs are black and white. There are black steps and there are white steps, and black steps and white steps. And you're trying to figure out what color the next step is, but you can't tell because you're in the dark. But there is a function that tells you what color the next step is if you know what step you're on, what the color is of the step you're on. But to know the color of the step you're on, you have to know the color of the step that you were on before, right? And that one tells you the color of the step that you're on, which tells you the color of the next step. So that's the idea of these recursive algorithms, that they're dependent on the information that is contained in them and the calculations that they actually make to make their next calculation. And they're functions that repeat themselves. And so you can use for loops, for example, to create a plot of a recursive function, where within the for loop, you have a for loop that's calculating something, and within that calculation, you use the calculation again, or use the function again, or whatever. This is the strange idea of recursive functions. But anyway, they're going to do some of this stuff, and it may not make sense mathematically to you. Doesn't matter. You don't have to understand the mathematics. You're going to, in the homework when you do this, you're going to just kind of follow the instructions and watch it work because it's interesting and fun to do. And then you can kind of play around with it and change it. So this is on page 566, example 14.1. Mandelbrot was a mathematician who studied these fractals. In fact, these are Mandelbrot. This is called the Mandelbrot set. And well, this is a plot of what is called the Mandelbrot set. And one of the things that fractals do is they repeat themselves. You can see that the overall kind of look of the image is repeated here. So here you have this big kind of bulbous thing with a smaller bulbous thing on it. And here you have a big bulbous thing with kind of a smaller bulbous thing on it. And if you look down here, you have a big thing with a smaller bulbous thing on it. And if you look at the very tip of one of these branches, you would see the same shape repeating itself over and over and over again. And that is a very common thing in fractals. And all of these are different types of fractals. This is another type of Mandelbrot fractal that's changed a little bit. It's got more complexity to it. This is not a Mandelbrot. Well, this one is a Mandelbrot, but it's a Mandelbrot that has some kind of a helical nature to it. So the math has been changed so that it gives us this strange twisting nature to it. You also have things like this. This is a different version of that same mathematics. It can be very, very complex. The more you zoom out, it can be very complex. The more you zoom in, it can be very complex. And then you can do all kinds of variations on this, all kinds of different variations. So let's take a look at some other fractals. These repeating kind of geometric mathematical things. In nature, you have these. This is the reason that they're so important mathematically, is because in nature there's a lot of fractal type things. Ice crystals, for example, are fractal repeating kind of things, and so that's a natural fractal pattern. There are also many types of shells that have a repeating fractal nature. It's just a smaller version of the bigger version thing. You have leaves that do this, trees, all kinds of things, coral. So many different things have this repeating nature. Even animals can have this strange repeating mathematical nature to them. That suggests that at the core of nature, there are these repeating mathematical constructs and I mean this is DNA essentially. DNA causes things to grow by doing the same thing over and over again on larger and larger scales, from a very small scale to a very large scale. And so that's why they become important. Although my favorite fractal is this one. This is the Tom Selleck fractal. Tom Selleck was famous for his mustache and his eyebrows, so they just made his mustache into his eyebrows. Okay, so anyway, that's the idea behind fractals, and what we're going to do with this is we're going to actually allow you to make your own fractals. Okay, so let's go ahead and clear some things out here. The beginning again, they're like steps 1 through 3, they're essentially just telling you the math of the Mandelbrot set. And now I want to get into the actual code of plotting the Mandelbrot set. So we've cleared everything out and we're going to call this thing iterations. I'm just going to call it iter, not inter. I'm going to call it iter instead of iterations. And I'm going to let that equal 80. So that's how many times we're going to do this, how many times we're going to run this fractal pattern math stuff. And we're going to define something called grid size, grid underscore size, which we will use as well. We'll let that equal 500. And then we're going to create a matrix of values and have two variables within this matrix, two variables within this. And each one of these variables is going to be a matrix. So that we're going to use the mesh grid function to do this. And this is going to give us some of our complexity here so that we can do some matrix mathematics. So we're going to make a mesh grid of this. And for the X part, we're going to do a linspace. So we're going to have linearly spaced numbers using the linspace command between -1.5 and 1, looks like. And we're going to do the same thing for the Y. Well, similar thing. So for the Y one, we're going to use the linspace command again. And instead of going from -1 to -1.5 to 1, we're going to go -1.5 to 1.5. Linear spaced. Linear spaced. And we're going to do this for the grid size. So grid size we already defined as 500. So what the linspace says is we're going to create 500 numbers linearly spaced apart between -1.5 and 1. And for the Y, we're going to make 500 numbers linearly spaced between -1.5 and +1.5. So each of these matrices should have 500 values in them. Should be 500 by 500 actually. The whole thing should be 500 by 500, I believe, in the end. And let's check to see if that's correct. See if we did that correctly. Oh shoot, I did something incorrectly. X, Y, mesh grid, linspace. I think I have too many parentheses. There we go. So yeah, so X becomes 500 by 500, Y is 500 by 500. And those numbers go in from -1.5 to 1 for the X in rows, and -1.5 to 1 in the columns as well. Makes this huge mesh grid of numbers. And then a very similar thing for Y, but going from -1.5 to 1.5 with 500 numbers. And if you want to look at them, you can. I mean, here's the Y. So it starts at -1.5 and then it just it goes all the way to, so sorry, going the wrong direction. -1.5 all the way down to, did I do that right? -1.5 to 1, Y, -1.5 to 1.5. Yeah. Should get to 1.5 here somewhere. Anyway. The mesh grid is 500 by 500, and that works, but you can look through them if you want. Now we're going to define a third variable C, or lowercase c, that's going to equal X plus I times Y. Now I times Y means that we're going to be using some, this is a complex variable. In other words, it has I in it, which is the square root of -1. You don't necessarily need to know why that is the case. Just know that it works and be happy with it. If you want to know more about that and you're interested in the mathematics of that, you can read more about Mandelbrot the Mandelbrot series or set many places online, but it's a mathematical thing. Then we're going to create another variable called z, and it's going to be a big matrix of zeros, the same size as x. Z equals zeros. And we're going to be putting some numbers into this thing eventually. The size of x. So these are just, this is like a placeholder thing. And then we're going to make a map. So this is for our color map. And this is going to equal zeros. Also the size of x. We're going to build our map as we go, I believe, if I remember correctly. And then we're going to put together our for loop. So our for loop is going to look like this. For k equals 1 to our iterations, which I called iter. For k equals 1 to iter, I'm going to do the following things. I'm going to let z equal z squared, dot squared, plus c. And that right there is the recursive thing. I'm using z to make a new z, right? But every time I go through, z already is something. And so I'm going to make a new z with the old z. So there's your recursive deal right there. And then I'm going to also find anything in anything that's in z. Each time I go through the loop, I'm going to look for anything in z that's greater than the square root of 5. So a is going to equal find the absolute value of z greater than square root 5. And I believe this is just for a limiting situation, because you don't want to jump outside of that, jump outside of the area that we're dealing with. Then we're going to map, we're going to call every time we go through the loop, we're going to define part of our map. So we're going to give map equal to whatever iteration we're going through. So the iteration that we're going through every time is called k. So map A will be called k. And that, so the first time we go through the loop, the first element in map will be 1. This will be 1. And then the second time we go through, it'll be 2, and then 3, and then 4, all the way up to 80, because we'll go through 80 times. So we'll end up with this map of k's, right? And then we're going to end our loop here. Whoo, that's a lot of numbers. I must not have. I think I made a mistake. I must have forgotten to suppress one of my outputs. I tried to suppress them all, but apparently it's calculating things, and it's taking a long time to print them to the screen. So I'm going to go ahead and interrupt that using my Control C and see what I did wrong in my loop here. What you definitely don't want to do in your loop is you definitely do not, oh, it looks like it's actually erased my last functions. But what I've done, I think, is I've created a recursion that's going to repeat infinitely, because you can see I've got a lot of infinities in here. So I should have done this all on a, I'm going to do this again, but I'm going to put it all on in a script so that I don't have to retype it all. I wonder if I can select multiple versions out of this thing. I think I can actually. So let's do that. Copy. Yeah. Okay. So I've got all of that in here. Enter a good size X, Y, Z, and okay, so what did this right here. So I didn't suppress that output, that's for sure. All right, so let's check and see if I did all the rest right and make sure I didn't make any mistakes. ITER 80, good size 500, XY equals mesh grid lens space mesh grid. That's two, I don't need that twice. That's good enough just once. I have too many there. C equals X plus I times Y, and that's correct. Z equals zeros, the size of X. Map equals zeros, the size of X. And then I'm going to go for K equals 1 to my iterations. Z equals Z dot squared plus C, that's correct. A equals find A, absolute value of Z greater than square root of 5, that's also correct. And then I'm going to create the map for K, map of A equals K, and then we'll end it. So that seems correct. Let's go ahead and put a clear at the beginning and a CLC at the beginning for good. And then let's run it. Entitled main root. Did it run it? Yes, it did. So all this stuff is here. Okay. So when I didn't, when I didn't suppress this one output, it was doing a lot of stuff. But when I did, because it was just having to print to the window, but when I did suppress it, it ran through the program fairly easy. So you can actually kind of see how printing things to the screen can be a major pain in the butt. But apparently it ran through the program because it's created all of these things now. And now what I want to do at the end of all of this is I want to actually make an image. So let's do an image of map. See what happens. There's my Mandelbrot image. And I can actually choose my color map. And I'm going to use the jet color map because it has a nice variety of colors. There you go. Now, in the next part here, we're going to actually change things a little bit because I've got the basic code here, but if I want to change what this looks like, I can actually change this function right here. This function, oh, sorry, not this function, this function right here. This function right here is the recursive function that changes what this looks like. So you can mess around with that. You can also mess around with this part right here, deciding what the map is going to look like. You can, of course, change what the colors are by messing with the color map. But they actually, the first thing that they do is they're going to create a new figure. So I'm going to do figure 2, and they're going to mess with this right here just by changing it. Changing it up a little bit after we've run the code. Then we'll go back and change the for loop code here in a second. Come on, dumb thing, there we go. So in this one, we're gonna call this thing multiplier equals 100. I don't know why they don't just call it 100, whatever. And we're gonna change map now to equal the absolute value of Z. times our multiplier. And you can change the multiplier to any number you want. But essentially what we did is we went through here is we created this map of values, and this map of values of 500 by 500 matrix. So it's got 500 by 500 pixels. That's 250,000 pixels, I think. Sound right? No, 25,000 pixels. But anyway, it's got a lot of pixels. So what I'm going to do is I'm going to take, I'm going to let map equal the absolute value of z, and the absolute value of z is also a 500 by 500. We're going to multiply that by 100 in this case, and then we're going to go ahead and image the map again. So we're changing what map is. I'm imaging it again and putting it here. So it's changing the color scheme going on. Now, in this one, we have it's kind of like blue and light blue, and that's it. There's like on, off, right? Yes, no. This one has variation depending on values in the matrix, in the Z matrix. They're actually going to zoom in using a bunch of codes here. So there's different ways you could zoom into this. You can use all this code, or you can actually just go in here and zoom in, right? When you zoom in here, you're going to see the pixelation. You can really see the pixelation quite easily, right? So it looks like there might be some great detail down here, but very quickly you see the pixelation. You also see that this is a definite color map, that each little pixel is a specific different color. There's not a lot of like scaling going on. It's not an RGB image. This is a definite color map. Or yeah, definitely using a color map. So it's indexed. Let's see. You can also zoom in by actually changing the code so that you're actually looking at, so that you're actually creating a map of a smaller version of this. So zoom in by actually doing the math on a smaller part of the map, a smaller part of the thing. And it will actually come out to look very much like this, very much like we did. Not like this, but like this. You zoom into this part right here, and you'll see something that looks kind of like this. And I don't really want to go through all of this to do it, but you can do it. That's what this code on page 569 is all about, is zooming in and showing that these things actually do have a very similar kind of nature to them. However, the thing that you are going to see differently is what you see on page 570. As you zoom in, you will see this shape connected to other shapes like this, and they will be moving in these kind of whirly twirly circle spirally things, and they show that on page 570. So you can actually see what it looks like when you zoom in, what all these little tendrils, but every time you zoom into them, you see just more of these things sprouting out. They all sprout out in kind of these twirly things. Don't have time to put all that code in, I don't think. We're supposed to be done at 3:30 here, is that right? Yeah. So we don't have time to write in all that, that code, because there's one other thing that I want to show you. And that is that this is a very simple function for the Mandelbrot figure. We can change this function. Let's instead of adding c to this, let's add c squared and see what happens. I'm going to do c dot squared, since c is a 500 by 500 matrix. And let's just see what happens if I run this now differently. So I've run it through, it's created new matrices over here. And if I go ahead and image the map, it looks different. It still looks very much like a fractal, but it's a different fractal. And you can do all kinds of things. Instead of doing c squared, z squared, let's get really crazy. Let's do z to the z power. Let's see what that does. And let's run that code. That starts to look really strange. Or let's do z squared and c to the z power. Oh, that one's starting to get really interesting. And you can see that it has incredibly complex structure, but there's still kind of a repetition going on here. You can see that if you zoom in on the pixelation here, if we could zoom in on this using code and do the math at a tighter, at a higher resolution, you might see something very interesting here. And that's actually what all of these fractals are. Every single one of these fractals is just a different version of this thing. If you just do minus ZC squared here, let's see, did we have, what was the original one? I can't remember, was it just plus C? So let's take off the squared, plus C, and let's do Z squared minus C. And let's run it that way. All right, remember the other one was pointed this way, this one points this way. Let's do a, put parentheses around this whole thing and multiply by Z. Well, that's not going to be all that interesting, but let's do it anyway. No, that one actually became too tight for us to see, so it's just plotting things everywhere. We'd have to zoom way out from that one, I think, to make it do something interesting. But let's do, let's see if we can find a new function that's more interesting. Let's do Z cubed and see what happens. And let's do Z to the 1/2 power, 0.5 power. This one actually, again, if you zoom into it, it has structure within this big sphere. You're not seeing it, but we don't have time to zoom into it that way. Trying to remember some of the different variations that start to get really interesting, and I can't remember them. Let's do the log of Z. Z equals the log of Z plus C, and see what that does for us. Oops. Yeah, that one didn't help us. That one probably had a bunch that got eliminated by the absolute value of less than square root 5. Let's try sine of Z. There we go. There's something kind of interesting, which means that this one will probably be even more interesting, I would imagine. Nope, not as well. Actually, this one has, you can't really see it on your screen very well, but right down the middle, there's a repeating. There are these. Let's actually use a new color map so we can see this, because this one is actually interesting. Let's use color map jet. Oh, actually, let's not. Let's use let's do this actually. Let's do this stuff right here. Oh, it didn't quite change it to what I wanted it to. But you can see that there's this repeating kind of like bubbly thing going on. And inside each bubble, they're repeating. What color map is going to give us that? Let's say color map. Let's use penumbra. What is it called? Can't remember what it's called. What is it? Parula. Let's see if that one gives us a different, it's not giving us variation, but there's like these ovally things, and then inside the oval, there are like these ovals that get smaller, smaller, smaller. But inside each oval, there's another set of ovals getting smaller, smaller, smaller. It's really kind of cool looking if you could see it, but can't really see it up there on the screen. So there's definitely some really fascinating fractal stuff going in there. So imagine, I mean, here's another example of a natural fractal that's very similar to the one that we just made there. Have you ever heard of infinity mirrors? Infinity mirrors are mirrors that are facing each other. And if you stand in the room, you will see things going on forever as the reflection goes back and forth and back and forth. Yourself, you'll only see one of because you're in the way of your other reflections, right? So you can't actually get multiple reflections because the light comes from you, bounces off the first mirror and bounces right back and hits you. So it doesn't hit the other mirror. But if you have somebody standing next to you, you can see an infinite number of them. And it's really quite cool. So this is what it looks like when you get into an infinity room. Let's see, they don't have a good picture. This is a decent picture, I suppose. Wish they had one of with just two mirrors. In most of these, they have mirrors on all the walls and the ceiling, which I think actually just confuses it. But if you just have them on two walls and you face them, it makes it better, I think. It's more relevant, I suppose, is a better way to say it. They don't have them. They just have these dumb ones that are them on all walls. That's annoying. Well, if you put them on all walls, then this effect happens in 2 dimensions, which I think is a little more confusing to what's really happening. But here's an infinity mirror room, I suppose. And I just wish they had one where it's only 2, because it's confusing to see how this goes for real. But that's the idea, is that this pattern repeats itself over and over and over. Here's another example. If you go into a room and take a picture of yourself, taking a picture of yourself, but you take a picture of yourself with the screen facing the mirror, right? So you use your camera, instead of looking at the screen, turn the screen the other way, use the camera to take a picture of yourself, and then the mirror will see a picture of you taking a picture of yourself. But in that picture will be a picture of the mirror taking a picture of yourself with the phone taking a picture of yourself. And in that image, another one will be happening. That's what happens in these things. And computer programs are the only way to really plot these things out. Did that weird you out? So this is the idea of a fractal, is that within the image is the same image. And within each of those images, there's another image. And within that image is the other image. And each of the images is the same embedded in the last one. And that's because of this recursive function that has itself in the function, right? It's what it is. I put Z inside the Z function. So it creates this recursive function. And this is a really useful thing for computers. Are the only way you can do this because of the infinite nature of this. Now, before computers were doing this, artists were doing this. Probably the most famous is M.C. Escher. M.C. Escher was very good at doing this, but he had a limitation that he's not infinite, right? So M.C. Escher was an artist at the beginning of the century, well, middle of the century, I suppose, and he did amazing fractal work, just amazing fractal work, all by hand, right? He also did really crazy stuff like this. Or the best one is probably his most famous thing is this one, which is kind of its own fractal. Let's see, which one do I want to choose? He did so many of these. It's probably this one. This is probably his most famous one. And of course, they animated the person falling down the stairs. But this is called the Infinity Staircase, or the Penrose Stairs. It's named for another artist who actually developed this the first time. But these stairs are always going down or always going up, depending on which way you go around them. And you can only draw this. You can't do this in real life. But in computers, you can do this. You can create this. right? Now here's something that'll really blow your mind. This will crack you up. Anybody ever seen the movie Inception? That's not right. That's not what I want to do. Penrose scene. So they actually built some stairs like this for this movie.
Shall we take a look at some paradoxical architecture? You're gonna have to master a few tricks. You're gonna build 3 complete dream worlds.
What kind of tricks?
In a dream, you can cheat architecture into impossible shapes. That lets you create closed loops, like the Penrose steps, the infinite staircase. That's it. Paradox. So a closed loop like that will help you.
So when you're looking at it from one dimension, it looks like it's an infinite staircase, but in 3 dimensions, it's not. This is why computers have to be used to deal with things like this, because in 3-dimensional space, we can't actually make it happen. We can make it look like it happens if we look at it from above in 2 dimensions. But if all of a sudden you change to 3 dimensions and rotate around, you realize that it's not possible. But a computer doesn't care. A computer doesn't care. A computer can do this kind of thing. That's the idea behind a lot of these, well, it's the idea behind all of these fractal kind of images. So computers and computer programs are extremely versatile, whereas the 3-dimensional world that we live in is not. Why does that matter? Because in science, it turns out there are things that behave like the Penrose staircase. There are things in nature that behave as if they're not, real, but they do behave that way. So if you have a computer, you can actually program the computer to behave like nature, whereas you can't really make a model to behave like that. Particularly, this happens in things that are subatomic, quantum mechanical kind of things. But it happens in other things as well. But that's a great movie scene. I just had to show that to you. All right, so we're done for today. We'll come back to the rest of this chapter and learn some more about working with graphics. Mostly we'll be doing plots after this instead of images. So we'll see you guys next week, and I will have some homework posted. You too. See you later.
Chapter 9.
Oh, yeah.
So maybe like we open for tomorrow. I'll do it tonight.
Yeah, I'll switch that for you. That's not the glass. Yep, I'll take care of it. So I have to go back a couple of weeks here, but I'll fix it.
Thank you.
Yep. No problem. There's no class on Friday? What's that?
Good Friday.
We still have class.
Oh, we still do?
Yeah.
Oh,
Yeah, class isn't canceled here for anything, hardly.
Okay,
So,
perfect.
Yeah, we do have class on Friday, so,
Okay, I can come
yeah.
sooner than that.
Yeah, the school will be open Friday and I should be here in the normal time. So,
All right,
all right,
and I'll try to be here. About normal work still, Friday.
let's see, am I gonna be here on Friday? Yeah, I should be here on Friday.
All right. Didn't know if you had to take it from home. That's why I was making sure.
I don't remember if I actually do have something that I'm going to do on Friday, but I don't think so. So it should be fine.
All right.
All right.
Thank you.
Yep,
Have a good week, Professor.
yep, see ya. After the due date. March, April. All right. Stop. End meeting.